Hello everyone, welcome back from the weekend. Glad to have you back. Today we are going to start chapter 3 and we're going to begin here with lesson 3.1.1. We're going to be focusing on equivalency to start off this unit and what it means for two functions to be equivalent to each other. All right, so our goals for today, students will identify equivalent and non-equivalent expressions using all representations. So when we say representations, we're talking about tables, graphs, and equations. Essentially are three main representations that we have for functions, right? The second thing we want to be able to do is we want to be able to use factoring and generic rectangles to verify equivalence. So that'll be part of the equation side of things, or the equation representation, showing algebraically that two things are equivalent. Or two functions, I should say. All right, so here we go. So it's a pretty simple question, right? We're going to be given two functions, and you can see our two functions here, f of x and g of x, and one of them is x squared plus 5x plus 6, and the other one is x plus 2 times x plus 3. So it looks like we have two parabolas here. One is in standard form, one is in its factored form, and what we need to figure out is whether or not these two functions are indeed equivalent. And you might make an initial decision here, and I always like to start off just by guessing, like yes or no. I mean, maybe yes, I think they're equivalent, or no, but I can't just say yes or no. All right, I have to have evidence, all right, and that's kind of the key thing here, is that we need to have evidence to back up whatever we decide. So if we decide these things are equivalent, I need to show that they are equivalent using evidence of some kind, all right? You can't just say things in math and expect people to believe you. They're going to check you every single time, all right? So we begin by collecting evidence. I'm going to look at the table for each function here. So I'm going to use my calculator to help me out with this. Okay, so I'm going to go over here to my calculator. I'm going to type on y equals. If you got anything in y1, go ahead and clear that out. And I'm just going to type in my function here for f of x. I'm going to type in x squared. So we'll say x squared plus 5x plus 6. And we'll go right to the table. So I hit second and then graph, and it'll take me straight to the table, and I can see a table being built here. So we'll just start with the table that they give us. We'll start at -5 and go to +5, see what we can fit over here. So I'm going to have -5, -4, -3, -2, -1, 0, 1, and 2. And then I'll grab all of the y values here. So we've got 6, 2, 0, 0, weird, 2, 6, 12, and then 20. Okay. All right, so I got my table for f of x. And now we're going to go take a look at our table for g of x and see what we've got going on here. So I'm going to go back to y1, and I'm going to clear that out. And this time I'm going to enter in g of x. So we've got parentheses, x plus 2. And then we have another parentheses and x plus 3. And I'm going to go right back to my table and see what I get. So I hit second, graph, and there's my table. So I'm going to get the same inputs, right? So whatever inputs you put in your first table, you want to make sure you put that in your second table too. So those are going to be automatic. All right, so -3, -2, -1, 0, 1, and 2. And then I go get my outputs here in the y column. So we've got 6, 2, 0, 0, 2, 6, 12, and 20. And so when I look at my two tables, this one for f of x and this one for g of x, they are in fact identical. So what do you notice about the tables? I would say, well, I notice they are the same. And you would think if the tables are the same, it would suggest that they are equivalent, right? So it would suggest equivalence. Okay, and this is really, we say suggest equivalence because, as you know, a table keeps going, right? I can keep clicking on the up button over here forever and ever and ever, and it'll never stop going. I have an infinite number of x and y values that are paired up here, and there is a real possibility that if I were to keep the table extending in both directions infinitely, that there might be one single point out there that might not be the same. We can't see the entire table at once. but based on what we're seeing here, just from this small portion of the table, it's suggesting that they are equivalent, but it's not a foolproof piece of evidence because we can't see every single input and output that there is. All right, so we need more evidence, right? So the next piece of evidence that we can get is our graph. We can take a look at the graph, which is another great piece of evidence. So I'm just going to go straight from here, and I'm going to hit the graph button, and I should see a parabola pop up, and there it is, right? So there's my blue parabola, and this is representing g of x. Remember, so when I go back to my y equals screen, I had g of x in there. So what I'm going to do is I'm going to graph both functions at the same time. So I'm going to put f of x here in y2. So I'm going to say x squared plus 5x plus 6. And when I graph this thing, you'll see the blue parabola come up first, and then we'll see the red parabola come in next. And if they are the same, the red parabola should lay directly on top of the blue parabola. There should be no difference between the two. So let's see what happens. So there's my blue parabola, and there's my red one coming in. And you can see it laid right on top of that blue parabola, which would suggest that they are the same, right? The red parabola matches up perfectly with the blue one. So it says hit graph button. What do you notice? Notice that they were the same again. So equivalent, right? And I'm still going to put a question mark on that. And it's for the same reason that we say suggest for the tables. And it's just because we can't see the entire graph. Like I can sit here and hit zoom out and get a bigger picture of the graph, right? And I can watch the blue parabola come down and the red parabola come down, and I can see more of the graph, right? So there's my red parabola coming in on top, right? I can see more of the graph, but I still can't see the entire graph because we know this parabola keeps going up and up and up forever, right? I'll never be able to zoom out and see the entire parabola because it's infinite, all right? So it looks like they're equivalent based on the table and the graph so far, all right? So the last piece of evidence that we need to confirm that two expressions are equivalent. Not that the table and the graph are bad or anything, but it just doesn't do a complete job. All right, so to get the complete proof, we need to show algebraically that they are the same expression. Okay, so what I'm going to do is I'm going to take g of x here, and I'm going to algebraically show that it's equivalent to f of x. And I'll show you how I do that. Okay, so this comes back to that second goal of using a generic rectangle to show that two things are equivalent, or two functions are equivalent. Some of you might have been wondering why I didn't just do this from the beginning, and that's fine. And the reason I didn't do this from the beginning is because I want you to see the power of the table and the graph. And the second reason is because I'm not going to factor here. Instead, I'm going to take g of x, and if you recall, one of the parentheses had an x plus 3 in it. So I'm just going to write that x plus 3 here across the top, and the other parenthesis, the other factor, had an x plus 2. So you'll notice that instead of factoring, I'm actually going the other direction. I'm starting with the outside numbers, and I'm going to get the inside numbers here. You might remember doing this from Algebra 1. So I'm going to multiply here, right? So x times x gives me x squared, right? And then 3 times x gives me 3x, and 2 times x gives me 2x, and then 2 times 3 gives me 6. Right? And then to finish this off, what I'm going to do is I'm going to take these four boxes that I see here, and I'm going to add them together. So I've got x squared plus 3x plus 2x plus 6. And then I can combine like terms. Notice the 3x and the 2x are like terms, so I can combine those. And we get x squared. And then if I combine 3x and 2x, I get 5x plus 6. Right? And if you notice what we got there, so when I multiplied those two parentheses together, you'll notice that what I got is x squared plus 5x plus 6. And if I go back and look at my f of x, right, that is what f of x is. So I was able to show that g of x is the same thing as f of x by multiplying its two factors together. Okay? So we have shown beyond any reasonable doubt that these are in fact equivalent. The table suggests it, the graph suggested it, and the algebraic proof verified it. Okay? All right, so let's try one more, and we'll be a little bit more concise, a little bit more quick about it this time. All Alright, so again, just kind of summarize what we're doing. We're starting with two expressions. I just want to show whether or not they are equivalent. So we're going to start with the table. And I put a little picture of the graph here. You don't actually have to graph by hand. Just use your calculator to verify that the graphs are the same or different. And then show me an algebraic proof. Okay, and so this is usually the most difficult part for the students right here. Is just the algebraic proof part, right? Show me algebraically these two things are the same. That's where students tend to struggle. Finding the table and the graph, students typically tend to do well with that. All right, so let's start with our table here. I'm going to go to y equals again, clear everything out, and let's just put them in one at a time for right now. And we'll start with this first one, x plus 3 squared minus 4. And let's take a look at the table. Okay. And I'm going to go down a little bit. I want to stay around 0 somewhere. I don't want to get too far away from 0. So let's do like negative 3 to 3 if we can fit that in there. So negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. That works. And we're going to go negative 4, negative 3, 0, 5, 12, 21, 32, and 45. Okay, so that is for this one, right? So if we were to call this one f of x, that's this table right here. So now this one we can call it g of x, and we'll put that one into our y equals screen here. Okay, so I'm going to go down. Actually, you can just clear this one out. We'll write it right over the top here. So we've got x squared plus 6x plus 5. And we'll go right back to the table. There we go. And we're going to start at negative 3, right? So negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. And let's look at our outputs here. So for negative 3, we got negative 4, negative 3, 0, 5, 12, 21, 32, and 45. So the tables are certainly suggesting that they are the same. So I'm going to go back and I'm going to take a look at the graph now just to make sure. So I should see one parabola coming down. And remember, the one that I have in there right now is g of x. So it's the x squared plus 6x plus 5 that's in there right now. So I got to put the second one in there, which is this one, x plus 3 squared minus 4. And we should see one parabola land right on top of the other. And graph. So we're watching for that red parabola. Yeah, and there it is. And it landed right on top of the blue one. I can't even see the blue one anymore because it landed right on top of it. So for graphs, I would say yes, they're suggesting that they are equivalent. Like I said, I do not want you to try and graph this thing by hand. Just look at it on your calculator and see if one lands on top of the other. Now, for the algebraic proof, if I'm looking at these two, this one is in its standard form here. This one looks like it's in its graphing form. And if you recall, one of the methods that we have for going from standard form to graphing form is completing the square. So I'm going to take this x squared plus 6x plus 5, and I'm going to complete the square and hopefully get the same thing that I see here in f of x. Okay, so here I go. Here's my box. Remember, we are completing the square here, not factoring. Okay, and I'm going to take the x squared, it goes in the upper left hand corner, and I'm going to take the 6x, I'm going to cut it in half, so we get 3x and 3x, and then I'm going to figure out my outside dimensions here. So we get x and x, and then x times 3 gives me 3x, and x times 3 gives me 3x, and then 3 times 3 gives me 9. All right, so if I were writing this in its graphing form, we would have x plus 3 squared, right, because we have x plus 3 and x plus 3 on both sides. And then I look at my n number here, and it's a 9, but I needed a 5. Right, so to go from 9 back down to 5, I would have to subtract 4. And now take a look at that. Right, this is an equivalent expression to what we had for f of x. It's x plus 3 squared minus 4. So when I completed the square, on g of x, I got the same thing as what I had in f of x, and that shows that they are equivalent. Okay, so you might make a note here. What we did was we completed the square. And keep in mind that you're not always going to complete the square to show that they are equivalent. Sometimes you factor, sometimes you complete the square, sometimes you just multiply. It just depends on the situation. So we're going to take a look at several examples over the course of the next few days where we see these kinds of things so that we can understand, like, hey, in this situation I need to do this thing, in this situation I need to do this other thing. All right, that way we can get our algebraic proof. But looking at the table, the graph, and what we saw here algebraically, I was able to take x squared plus 6x plus 5, use completing the square to get x plus 3 squared minus 4, showing that they are the same. All right, guys, that's it for today's lesson. Get the practice problems done. Let me know if you have any questions in the Zoom chat. Have a great day.